and you may be familiar, let me see if I can use my pointer over here, you may be familiar with CIQ as the company that supports and is kind of behind some of the development of Rocky Linux. You may also know that CIQ is also supporting some of the open source projects like Apptainer and Werewolf. My colleague, Jonathan Anderson, is going to be talking tomorrow about Werewolf at 3:15, so please be sure to attend that talk as well. And there's also a few other products that you might not be familiar with. One that we announced earlier this month called Mountain, that I'm not really going to talk about too much today, but it's a cool product. And then also something that I'm really excited about is going to be released during this meeting, actually on Thursday, and that is Fuzzball. And I will talk a little bit about Fuzzball towards the end. But today, for the most part, I'm going to be talking about Apptainer, in particular, how to get the most out of Apptainer, how to use it to make your life easier. And it's kind of a quick talk, so I'm not going to be going into a great deal of detail, but we're here, the entire week if you guys want to talk to us. All right, so this is a HPC conference, so most people here are probably familiar with Apptainer at this point in time, so I probably don't have to tell you like every little detail about the origin story, but just to level set, how Apptainer came to be is that around 2015, we in the HPC community identified a big need for containers within this space. And so Singularity was designed by Greg Kurtzer and others in the community with HPC in mind. And this is the only, not the only, it's kind of, it's different in that space in that it's a container solution that was really designed with HPC in mind. In late 2021, in order to make sure that Singularity remains free and open source software forever, some of the community members got together and formed an advisory board, and Singularity entered the Linux Foundation. And as part of that entrance to the Linux Foundation, it changed its name to Apptainer to avoid confusion with similarly named projects. So that's basically how Apptainer came to be from its origin as Singularity. Okay, now, once again, this is an HPC conference. Most of you already know that Apptainer simplifies your life, and it's been doing so for a long time. I'm going to review some of the ways in which it does that, and I'm going to talk about some new things that we're developing and some new strategies you can use as well. So, first off, Apptainer really was one of the first container platforms to support GPUs. So we were kind of a pioneer in that area, and that obviously makes your life a lot easier. More recently, Apptainer has begun to support unprivileged builds, which means that you don't have to be root anymore to build a container. You can pretend to be root inside the container and do what you need to do. It also now supports unprivileged installations, and I'll talk about all these in a little bit more detail in the coming slides. And finally, I want to talk a little bit about MPI support. This is something that Apptainer has supported for a long time, really just because of its architecture. But I want to talk about some new kind of tips and tricks that we've recently identified, and just kind of talk about how you can make MPI a little bit easier in your containers. So GPU support. If you're using GPUs with Apptainer, then you know that you can just pass the --NV option if you've got a NVIDIA GPU, or you can pass the ROCm option for AMD. And essentially, Apptainer just goes ahead and locates and bind mounts all the different libraries that it needs into your container at runtime to make the GPU work. And this is great because it keeps your container portable. So kind of counterintuitively, what this does is it allows you to move your container from one system to another with a different GPU driver, or it allows your system administrator to update your GPU, and your container will just continue to work. You don't have to rebuild the software inside of it just because the driver changed. So yeah, that keeps your container portable. I mentioned before that we now support unprivileged builds, leveraging rootless user namespaces. So basically this requires an up-to-speed kernel that supports the user namespace, but it allows unprivileged users to build containers. Even if you're using things like DNF or Yum or apt or some other package manager inside, even if you're writing to places that are part of the root file system, you can still build these containers without any root privilege. This is convenient, obviously, because now users can build their containers anywhere. But another thing that you might not think off the top of your head, it's a lot more secure. And this is something that we've been kind of trying to impress upon the community for a while, is that if you are building your containers as root, that's actually an inherently unsafe and inherently kind of risky thing to do. And so in the past, we've suggested that the best thing to do is spin up a disposable VM and build your containers then and then throw them away. This makes it so that you don't really have to do that anymore. You can build your containers without worrying about the malicious contents of some container messing up your host system. Not only is it now possible to build your container without privilege, but it's also possible to install Apptainer without any privilege. So this is another pretty new feature. In the past, it used to be that you had to have a root-owned set UID bit as part of the Apptainer installation, which would elevate your privileges for some of the operations carried out by the runtime. But now that's no longer the case, and in fact, if you install Apptainer just with the default configuration these days, it's going to be unprivileged by default. That's just the way it installs now. This also means it's possible for somebody other than root to install Apptainer. Normally you would use a package manager like DNF or something to install Apptainer, but you can actually just install it yourself. And in fact, we now ship a convenience script in the Apptainer GitHub repo that allows you very easily to install Apptainer in a relocatable way, in an unprivileged way. So this is a pretty new feature that Apptainer is, now supports. Okay, now I want to talk a little bit about MPI integration. So I've been kind of going through these topics really rapid fire and quickly. I want to slow down for a little while and spend a little bit more time talking about MPI. So MPI support has been part of Apptainer for a long time. It's one of those things that makes your life easier. But in the case of MPI, it makes your life a little easier, but maybe not that much easier. MPI can be kind of tricky to implement within a container. So the reason for this is because if you try to spawn an MPI job from within a container, what it does is it SSHs out to a bunch of other nodes or whatever, and then it tries to execute the command that it's supposed to execute, and it finds that command isn't on the system because it's in a container. And so it gets out of the container and then it doesn't know how to get back in. So historically, we've suggested that the best way to do this is that you need to have an MPI installation on your host system, and then you have to match either the same or a compatible version of MPI inside the container. And what you'll do is you'll spawn your MPI using the host system MPI, and then that'll work in tandem with the containerized MPI, right? So there's a few different models for how to do this. The hybrid model is probably the most common, and this is like straight from the Apptainer documentation. But in this model, you'll actually install MPI directly into your container, and you'll match as closely as possible the MPI which is installed on your cluster, and then hopefully those two will be compatible with one another and will work properly. The bind model kind of does the same thing, but instead of installing MPI into your container, you'll just bind mount all the bits and pieces from the host system into the container at runtime. So this kind of makes sure that the two are identical. And then I'm going to talk a little bit about a third way that we've recently identified. Jonathan actually did a lot of this work, and I'm just kind of ripping it off and presenting it for him. But this third way leverages a tool called PMI, or a standard called PMI, which allows you to spawn your containers without actually needing an MPI to do so. So I'm going to talk about that in a minute. First, let me talk about the old way to run MPI. Okay, so to do this, I don't really have a demo. I've got more like a visual aid. So I carried out this work in an environment, just a little kind of test cluster environment that we have where we've got access to Slurm and some other stuff. But basically, what I wanted to do is I wanted to figure out how hard is it really to run MPI within a container. And so on the Apptainer documentation webpage, there's like a definition file, example definition file for installing OpenMPI. I use that as a starting point, and this is the result of that. I'm not going to go through this in detail. The basic thing that I want you to take from this is this was really a difficult exercise. This was a hard thing to do, to create a definition file which containerized MPI properly to run within this system, okay? So I've got this little MPI Hello World program, and that's what I want to run just for test purposes. Oh, wait a minute. This is not the right def file, I'm sorry. I saw confused faces, and I wondered why everybody was confused. I'm in the wrong directory. All right, sorry about that. So this is the definition file I wanted to show you, one that illustrates the hybrid approach of actually installing MPI into the container. Okay. That looks better. Okay, so I've got this little MPI Hello World thing that I'm going to be compiling, and that's going to be my test here. Most of this just comes from the definition file, which you can find in the Apptainer documentation. But if you go down here to this DNF, you can see I'm installing a lot of different things with DNF right off the bat. If I go down here a little bit further, let's see. I'm actually, so in this environment where I'm doing this, we actually have an open HPC installation, and we install a lot of libraries, a lot of tools using OpenHPC, which is great and convenient and easy, but in order to compile against the same libraries, I actually have to install OpenHPC inside the container as well, and then use DNF down here to install a lot of the same tools that we had on the host in the container. So it's getting kind of complicated. And then if we get down here to the configure statement, you can see that there's like kind of a crazy custom configuration that I had to do. And now this took me a long time to create this, and kind of the kicker is, I was also the one who installed OpenMPI on this host. So I knew very well how it had been installed and how it was configured and what it was linked against and all that kind of stuff. And it still took me a little while to do this. Now, if users don't really know all the ins and outs of how MPI is installed on your host system, this is going to be a really difficult task for them. Now, obviously, once you do it once, it becomes a little easier because you can recycle this a lot of times. If you're an administrator, you can make this a little easier for your users by actually creating a base container for them, you know, and have them start from that. But still, this is not ideal, and it's also not super portable. This container is going to break if the OpenMPI version changes on the host, or if you move it to another cluster or something. So it's not ideal. Let me look at the bind model. So you would think intuitively that the bind model would be, howdy, come on in, no, you're good. I get that a lot. So, you would think that the bind model would be simpler, right? Because it's all you're doing is you're taking all the bits and pieces that are on the host and you're just bind mounting them into the container. And it is simpler if you just look at the definition file, right? I will point out that in this case, I can't so in the previous case, I copied the MPI Hello World, actually C like code into the container, and I compiled it inside the container. I can't do that here because there's no MPI inside the container, so I have to compile it on the host and then copy the compiled binary into the container, right? So that's a little bit wonky. This environment, it looks complicated, but it's not really that hard. All you've got to do is load the module, and that gives you an idea of, you know, what the environment should look like inside the container. But where the real complication comes in with the bind model is look at this job submission script I've got. Look at that Apptainer bind path for a second. That is bananas. Okay, there's no getting around that. That's a mess. To make things easier on myself, I just went ahead and I bind mounted all of opt OHPC into the container, which worked, but could break stuff, who knows. And then if you look past that, you'll see there's all these system libraries that MPI is compiled against. All these user lib64 system libraries that I had to bind mount into the container. Now you don't want to do that. That's a bad idea. This worked in this case because my glibc inside my container was the same as the one on the host because I was running the same OS in the container as I was on the host. But there's no guarantee this is going to continue to work if your containerized operating system is different from the host operating system. And I want to point out one additional thing. If I'm compiling my MPI code on the host and then just copying it into a container, and then I'm taking all the MPI and the libraries and everything and copying them into a container, what am I using the container for? Right? What's the point? So Okay, so those are the kind of the old ways to do containerized MPI that are not super great. Well, now I want to talk about a new method that once again my colleague Jonathan first identified, and it's not new in the sense that these tools are new. They've actually been around for a while, but it's new in the sense that we've recently identified this as a good strategy, and we think this is a better way now that some of these tools have matured to try to use MPI in your container. So there's this thing PMI, which is a series of standards. And the standards basically say, this is how we think that MPI processes should do wire up, this is how we think they should be launched, and so on. So because these standards exist, and I say this series of standards because there's PMI, there's PMI2, there's PMIx, and PMIx's version, so it's still not super easy, it's still a little complicated. But because this series of standards exists, you can do something like have your MPI inside your container have PMI support, and then have a tool, not necessarily MPI, but have a tool on the outside of the container that also implements the same kind of MPI standard. And then you can use that tool to launch your containers. And if you do that, MPI on the host becomes irrelevant, which is really nice. In fact, you don't even have to have MPI on the host anymore. Okay, so let me show you what that looks like. So once again, let me go up here now to my different directory. So I believe, I haven't conferred with Jonathan about this, but I believe that his original intent in doing this work was to look at SPAC and to use SPAC. Is this correct?
That's what I do.
Okay.
It wasn't necessarily the original intent, but
okay.
Yeah.
So Jonathan was using SPAC to create containerized MPI applications, and here's a very, very simple. Well, so SPAC. So I'm introducing a bunch of stuff at the same time. SPAC is a package manager for HPC, which basically installs everything from source. So it compiles everything, and you set up a compiler tool chain, and then you do this with YAML files. It's very, very simple. And SPAC actually supports containerization. So in this particular instance, what we're doing is we're installing the OSU Micro Benchmarks MPI suite, and then we're doing so with OpenMPI. And we're giving it a few things that we want this OpenMPI to support. In particular, PMIs here, that's important. And then we're also installing libfabric, and we're specifying some protocols that we want libfabric to support. The kicker here is PSM2, that's the important one for this cluster because we use Omnipath, and Omnipath is supported by PSM2. All right, so then here, this stanza basically says, oh, and I want you to containerize this, and the way in which I want you to containerize this is to build a Singularity container, and then there's some details about the container. I'm not going to go through all of them. But in any case, once you've got that YAML spec file, you can run a command within SPAC to spit out a definition file. So I've already done that. I'm not going to actually show how that works. It's very, very simple. But this is the definition file I erroneously showed you earlier. But once you've got this definition file, you can actually just edit it too. That's another thing that you can do. So I liked this definition file, but I wanted also to have this MPI hello world test. So I just went ahead and used the file section of the definition file to add that in. And then down here at the bottom, I compile it. This definition file is actually really cool. I'm not going to go through all the details of it, but if you're interested in it, ask me about it later. It's got a bunch of optimizations that are pretty neat that I just don't have time to cover today. But in any case, once you've got that, so now remember this thing has PMI support. Now, I'm just running this on my laptop. I don't have access right now to the cluster where I did this work, but I did pre-record a demo for you, so I'm just going to go ahead and play that back with Skinema. So I'm going to go ahead and play that. So on this cluster, I went ahead and I just got rid of the MPI. So I'm going to demonstrate first, I don't even have MPI on the host system, right? So which MPI exec, which MPI run, those are not on the path. They're not on the host. Okay, so the next thing I'm going to do is I'm going to show you, so this definition file, this contained OMPI, I've created a container from that. And so now, because that has PMI support, and because I have PMI support in Slurm, which is also important, I can use srun to just go ahead and launch this containerized MPI process, and it's going to know how to do wire up through PMI. I have to specify to the srun command that I want the MPI flavor to be PMI2, because that's what this particular version of Slurm supports, is PMI2. And then after that, it's just, set up the number of tasks, set up the tasks per node, and then I'm gonna just go ahead and call Apptainer, and I'm gonna say exec. So I want it to execute something. I want it to execute something in that contained ompi.sif container, and all it's gonna be is that MPI hello world. And you can tell I type really slow. It takes me a long time to get anything done.
While you're typing, do you need the same flavor of PMI in the container as in the outside? Like, you specified PMI2 here. If you specify PMIx here, it would fail, presumably.
So it would have failed, but the reason that it would have failed, so I think that the container has PMIx support just by virtue of the fact that we added the PMI flag to SPAC. I'm not sure about that. I think it's the case. But the reason it would have failed is because this version of Slurm doesn't have PMIx. And the reason I found out at Oak Ridge that this version of Slurm doesn't have PMIx is it's got currently a vulnerability in it.
Ah, okay.
So it's not an accident they left it out.
Yeah, we're using the version of Slurm that's in OpenHPC for this demo, and so we just based it on whatever support happened to be there.
Gotcha.
But yeah, the MPI inside the container can be compiled with multiple PMIx versions supported.
So you can see that my little hello world did its thing. It started 2 processes with 2 different ranks. I'm going to go ahead and run it again, and I'm going to provide an environment variable which makes it more verbose and gives me some information about the high-speed interconnect that it's using. And then I'm going to take, that spits it out into standard error. I don't really know why. But I'm going to take that standard error and I'm going to grep it for the keyword open. And that's going to tell me that not only did this container run a fully containerized instance of MPI, but it actually used that PSM2, that OmniPath adapter to do it. So that's pretty cool. And this is a lot simpler, it's a lot more robust, it's a lot more portable. It's just a better, cleaner way to do MPI inside the container. Now, I'm going to caveat this by saying that the reason that high-speed interconnect worked, I don't think that that's a given. Okay? I think that it worked because we have similar tools installed on this host and within the container. So you still could run into some trouble with your high-speed interconnect not working. That gets into kernel modules and libraries that match kernel modules and stuff like that. I'm not going to cover that in detail, but still, I think you're on much firmer footing if you've got this wire-up problem solved, and that's one big hurdle you've overcome already. All right. Oh, yep, and I just did the demo. Okay. So, and once again, I covered that in like 10 minutes, and I left out a ton of details. Jonathan, so we gave a talk jointly, like a 3-hour talk, which was crazy, to Stanford University with their
HPC
AI Advisory Council meeting. And that's up on YouTube, and the second hour is Jonathan going through basically this in a lot greater detail. So if you want more details about this, I highly recommend that you watch his talk.
I totally forgot that was on YouTube.
Yeah, it's on YouTube. Okay, now, I've got like 6 minutes left, and I've been talking all about containers. And in this day and age, if you are talking about containers and you don't cover orchestration, then you're doing something wrong. Like, container orchestration is a very, very big deal, right? So no modern discussion of containers is complete, yada, yada, yada. All right. So I would posit, though, that existing container orchestration solutions have really not been created with HPC in mind. They've been created for services. Specifically, they've been created with microservices running in a cloud-native architecture in mind, okay? And I'm looking at Kubernetes in particular when I say this, but there are other tools as well that have been designed with that mindset. And because of this, they include features which are not relevant to us users who want to run jobs in HPC environments, okay? And You could say, okay, well, who cares? You just don't use those features. Problem is, you still have to learn about those features to use these tools. You got to know all about them, right? They also exclude features which are relevant to us scientists who want to use HPC with orchestration. So we really need a method to orchestrate, not services, but to orchestrate jobs. Now, a lot of times in HPC, we use Slurm or a batch scheduling system like Slurm to do our orchestration, so we don't really worry about it too much. But increasingly, we're moving away from on-prem HPC clusters. We're starting to branch out to the cloud and do HPC in other places, and then it becomes a big glaring issue, right? That you need to have some sort of tool to perform orchestration. And so that's Fuzzball. That's what we're going to be releasing on Thursday. That's the new product that we're going to be unveiling pretty soon. It says I'm going to give you a demo of Fuzzball in, let's see, 4 minutes. I'm just going to give you like a little teaser trailer of Fuzzball here. So Fuzzball has a command line interface, and it also has this really shiny, pretty web UI. I'm going to show you the web UI because it's a little easier to explain and kind of see what's going on. But bear in mind that you can do everything that you can do with this web UI, you can do with the CLI too. Okay. All right. So I should also explain that this version of Fuzzball is running on AWS. So this is actually a real instantiation of Fuzzball, which is running. And what it's doing is it's a service which is hanging out, waiting, and listening for somebody to submit a workflow. And when you submit a workflow, you do that with a YAML file. And so then it says, oh, okay, well, you've told me that you need these resources, this many CPUs, this much RAM. I'm going to go out and spin up those cloud resources for you. I'm going to grab the containers that you need to run this job. I'm going to kick off your processes inside of it. I'm going to set up any dependencies that you've got. I'm going to take your S3 buckets or whatever storage that you've got and map those directly into your jobs so that you can access your data and you can write it back out. And then I'm going to tear everything back down again so it's not sitting around wasting your resources. That's Fuzzball in a nutshell. So I'm just going to show you really quickly. So here I'm showing all the workflows that the people in my group have run. Most of these are run by Forrest Burt, who's a super smart, awesome guy. I'm just going to show my workflows for a second, and that's so I can quickly and easily find this MPI Hello World, that demo that I just showed you. I actually ran it in Fuzzball as well. And so if you look at the logs from that, you can see that this ran 2 different ranks. Now we're looking at IP addresses instead of host names because we're running in AWS. But yeah, it ran 2 different ranks. And let me show you how easy this is. So I can open this workflow in this editor. This is like a drag and drop kind of thing where you can move multiple different jobs around. You can set up dependencies between them. You can do all kinds of cool stuff like that. You can also click into the job, and then this is where you configure everything. So the job's name is here. The command that I want it to run is MPI Hello World, the same as its name. The environment specifies what the container is. So everything that runs in Fuzzball is containerized. And this is the container that I want. This container is actually up on Google, and so I need some secrets to be able to access the container. And Fuzzball allows you to manage secrets in a really nice and secure way. But what this all actually boils down to is a YAML file. And so I could just pop open Vim and I could just write all this stuff in a YAML, and then I can just submit it that way too, if that's what I'm interested in doing. Okay, so in addition to, so the way that the MPI works is here in resources. Maybe it's not in resource. Actually, here in the job type, you say that you want this job type to be multi-node. You could also have a task array if you want like an embarrassingly parallel job. And you can specify that you either want OpenMPI, MPitch, or GasNet. And I also want to show you really quickly, I'm going to go back. I'm going to show you really quickly a more complicated job. This job actually didn't finish successfully because the S3 bucket that I had at the end actually didn't exist. But that's no big deal. It just shows that you can map an S3 bucket to it if you want to. And this one I want to show you because this illustrates the idea of a job dependency, right? So you can set up these directed acyclic graphs of jobs. And in this case, I've got one container that I'm just going to use to create a bunch of directories. Then once I've got that container run, I've got another couple of containers that are going to download data. Once I've got the data downloaded, I'm going to go ahead and make a database using Blast, which is a biomedical application, and then I'm just going to go ahead and run it. And you can see how this, you could fan out and have hundreds of jobs running underneath of a single one, and then fan back in, and do like map reduce kinds of things with this orchestration tool. Okay, so that's just oh, and also I should mention that you can easily use GPUs as well, just by specifying in the resources that you need. Let's see.
Is it under devices?
Yeah, probably. Oh, yeah. By specifying here that you need a GPU and the number of GPUs that you need and so on. I thought this job ran with GPUs, but I guess not. Okay, so that just a really, really quick little taste of Fuzzball. We're going to be releasing that on Thursday once again, and so you'll soon be able to use it yourself. So just to kind of sum up everything I've told you, so Apptainer was created to fill a need in HPC for containerization. It was purpose-built really for HPC. As you all know, it makes your life easier, and it's continuing to do so with new features that we continue to develop. And Fuzzball, now, just as Apptainer was originally created to fill a need for containerization in HPC, Fuzzball is now being developed to fill the now glaring need for orchestration in HPC. Okay, and that's it. Thanks very much. I'll take any questions. I understand I went a little over time, so if you want to just talk to me or Jonathan later, we're going to be at that CIQ table in the main hall also for the rest of the week. But I'll take questions now too. I think Kelly, you got a question? Oh, yeah, Jan.
Sorry. Yeah, thank you. Great presentation, thank you. So, quick question about Fuzzball. I understand that it's more for jobs that can run services, right? Do I need to run Kubernetes and Fuzzball if I want both of them, or if I want basic services?
We've been talking a lot about this. I mean, it has been at this point purpose-built for HPC,
Sure.
and so because of that, so Fuzzball runs on Kubernetes.
Okay.
Because that's the best. It's a microservice. It's in a cloud-native architecture. It's sitting there up on AWS and waiting for YAMLs to be submitted to it, and doing stuff based on that. And so for that type of service job, Kubernetes is better. But for jobs, Fuzzball is better. And I don't know. I mean, I'm sure we've talked about it.
Yeah. So the reality is, like, Fuzzball is developed by requirements from people that we're working with who are using it, and that is a need that is expressed. So it's something that's being worked on. It's not the next thing we expect to release, but it is pretty close on the list.
The reason I asked, right, is it's just a job can quickly turn into a service in
Sure.
some ways, right?
Yeah.
Well, so there's that, and other things that we've seen come up is there's the whole the science gateway use case. So there's the idea of having a science gateway that's maybe running as a service in Fuzzball that spawns off jobs as part of this workload, or maybe you have a data provision service like a database or something like that that you then want to run jobs against. So those are the kinds of use cases that we've been looking at, but we don't have a date on it yet.
Gotcha. Awesome. Thanks.
Yes, sir.
Do you support other types of programming languages in Fuzzball, or techniques like PS type programming languages, like Chapel or?
Oh, yeah, so Chapel runs on GasNet. So So we've run Chapel jobs within Fuzzball, and that was actually the reason that we implemented GasNet as one of the different. It's not really MPI, but one of the different multi-node flavors that you can run. Yeah, and it's I think that's a pretty good list at this
unique
point
in this
time.
kind of.
Yeah.
Yeah.
So I don't really know what else you would support, but as other things are developed, we would continue to add support to those as well.
Keep asking.
Sure.
So sometimes Singularity containers get pretty big, which adds to the build time with them. Docker obviously has some kind of layering system, and I mean, with container, with Singularity or Apptainer, you can kind of build a SIF and then build another SIF on top of that SIF.
Yeah.
But that also requires a bunch of def files and a bunch of linking to SIFs. Is there some kind of plan, or has there been conversations about some kind of building layering process built in so that building is a little faster at times. It's like I'm building machine learning containers and all of a sudden like, oh, it's taking me forever to just add one package sometime. And that's not your fault, the package is big. I'm just curious, like if there's been some conversations about layering and speed.
Yeah, I mean that's something that we've been talking about, or people have been talking about with Apptainer for many years. But I mean the fundamental idea is so radically different that it's not really there's not really a good way to kind of So what I suggest is that when you're first developing your container, the best thing to do is to create a sandbox, which is a writable. It's just a bare directory.
Yeah.
And so, and then to make your changes in the sandbox, and that way every change you make is just there. And then record all those in your definition file, and then only build the def file kind of like at the end after you're sure that you've got everything just the way you want it. But I think what you're saying is I've got a container I've been using for a long time. It's awesome. There's another Python package that I want in the container. I have to rebuild the whole thing from scratch. Yeah, there's not an easy way around that because you could just create a definition file to build that base container.
Right.
And so, but the definition file is something that gets saved in the metadata inside the container. And if you do that, all it's going to say is, I built from this base container and I added this one thing. So then if you want to go back and rebuild that container, or somebody else gets it and they want to know what's in it, it doesn't help them at all, So, I mean, you could, if you're trying to do like one-offs and kind of, something quick, you can totally do that. You can build from your existing container. And you can do that also, I don't know if you're aware of this, you don't have to use a registry or anything like that. You can just build from it on disk.
From the SIF file.
Yeah.
I have a recommendation on that, if that's all right.
Sure, go for
So
it.
what Apptainer is many things, but the most of its benefit is in the runtime engine. The way it does mounts and sets up your the actual physical container. The SIF format has a lot of like performance benefits and things like that. But there's no reason you have to use all of Apptainer's stuff. So what I like to do is define my container as an OCI image. And you can build that with anything, get all of the benefits of the layering that you get in that, and then you can just pull it as a SIF when you want to run it, right? And use it as the runtime, but not as your development specification.
Okay.
So I will asterisk.
Yeah,
that.
go for it.
So there are some features of SIF files which I think are underutilized.
Yeah.
Those include things like signing and verifying your containers. Software supply chain, I don't think people realize what a big issue it is yet. I think it's going to take some malicious actors to own some folks before people realize what a big deal it is.
Was one of the hack last year or whatever it was, right?
Yeah.
It happens a ton.
So you can do that with a SIF file. So you can push it to an OCI registry like Docker Hub or something using the ORAS protocol. And then when you pull it down, you can make sure nobody's tampered with it by verifying that signature on it. There's really nothing like that right now if you're using OCI images with Apptainer. The two of those don't allow you to verify the contents of what you got. So, and then there's other things like you can encrypt containers, you can encrypt SIF files, you can run them encrypted and do things like that. I mean, unless you really need that, unless there's a special use case, you wouldn't use that. But all I'm trying to point out is that the SIF file format, it's got some advantages over OCI. And if you get locked into creating Docker files and building everything with OCI, you might go down a pathway that you might miss out on some features once they start to be more widely adopted.
That makes sense.
Yep. It's like, I got 6 minutes to get to the next talk, which I guess would be fine. But if there's any other questions, I can hang out and take them as long as you got them. Thanks again.